places in the universe where the rules don't just bend, they collapse, where cause and effect lose their meaning, where space and time trade places, where even our best equations stop making sense. Black holes are one of those places. We're told they are cosmic death traps, that crossing their boundary means instant destruction, that nothing, not light, not matter, not information, can ever return. But here's the uncomfortable truth. Physics no longer agrees on what happens inside a black hole. And some of the most serious theories suggest that falling in may not be the end of the story. When people imagine black holes, they picture a violent edge, a glowing boundary that rips anything apart on contact. But that image is wrong. The event horizon is not a surface. It's not a wall. It's not a barrier. It's not even something you could see. The event horizon is a point where escape becomes impossible, a region where the speed required to leave exceeds the speed of light. Once you cross it, every possible path through space-time leads deeper inward. But crossing it doesn't necessarily feel dramatic, and that detail changes everything. For small black holes, the danger comes early. Long before you reach the event horizon, tidal forces become lethal. Gravity pulls harder on your feet than your head, stretching you into a thin stream of atoms. Physicists call this spaghettification. It's as unpleasant as it sounds, but supermassive black holes, the kind found at the centers of galaxies, behave very differently. Their gravity is immense, but spread out over an enormous volume. Near the event horizon, the difference in gravitational pull across your body can be surprisingly small. In fact, if you fell into the supermassive black hole at the center of the Milky Way, you might cross the event horizon without noticing anything at all. No tearing, no crushing, no warning. From your perspective, nothing special happens. That's the first crack in the story we tell ourselves. So if entry doesn't kill you, what does? According to classical physics, once inside, escape is impossible. Not because your engines aren't strong enough, but because out no longer exists. Inside the event horizon, space and time swap roles. Moving forward in time means moving closer to the center. Avoiding the singularity would be like trying to stop time itself. Every future leads inward. That's the classical answer. But classical physics breaks down here. And when it breaks, strange possibilities emerge. One of the oldest ideas comes from Einstein himself. In the 1930s, Einstein and Nathan Rosen discovered that the equations of general relativity allow for tunnels through space-time, structures now called wormholes. In theory, a black hole could be connected to a white hole, an object that expels matter instead of consuming it, fall in on one side, emerge somewhere else. These tunnels, known as Einstein-Rosen bridges, aren't science fiction inventions. They fall straight out of the mathematics. The problem is stability. According to the equations, these wormholes collapse instantly. Anything trying to pass through would cause the tunnel to pinch off before it could escape. So the door exists, but slams shut immediately, unless something holds it open. In the late 20th century, physicists proposed a radical solution: exotic matter. Exotic matter would have negative energy density, a property that sounds impossible, but isn't forbidden by quantum theory. In fact, small amounts of negative energy have already been measured in laboratory experiments through a phenomenon called the Casimir effect. With enough exotic matter, a wormhole could remain open long enough to traverse. The catch? The amount required would rival the energy output of stars. We have no idea how to create it, no way to store it, no idea if it can exist at macroscopic scales. But the equations allow it, and that matters. Then there's a quieter, more disturbing possibility. In the 1970s, Stephen Hawking showed that black holes aren't completely black. Quantum effects near the event horizon allow energy to leak out in the form of radiation. Over incredibly long timescales, black holes evaporate. This radiation isn't random. It carries information, and information, according to quantum mechanics, cannot be destroyed. This creates a paradox. If you fall into a black hole, where does your information go? One possibility is that it is slowly encoded into Hawking radiation and released back into the universe over trillions of years. Not survival in the usual sense, but not total erasure either. In a deep physical sense, nothing that falls into a black hole is truly lost. And then things get even stranger. Most real black holes rotate. These rotating black holes, called Kerr black holes, have a far more complex internal structure than their non-rotating counterparts. Instead of a single point-like singularity, the mathematics predicts a ring-shaped singularity. And under certain conditions, the equations suggest paths that avoid the singularity altogether, trajectories that pass through the black hole without being destroyed. Where do they lead? The math allows for exits into other regions of space-time, other universes, other times. We have no evidence this happens, but we also have no proof it doesn't. Testing these ideas would require sending something into a black hole and somehow retrieving information from the other side, a task far beyond our capabilities. And then there's the most controversial idea of all. What if the event horizon isn't gentle? Some physicists argue that quantum effects could create a high-energy firewall at the boundary, a region that incinerates anything attempting to cross. If true, it would restore black holes as absolute death traps. But firewalls come at a cost. They violate one of the core principles of relativity, that free fall should feel like floating in empty space. If firewalls exist, much of modern physics must be wrong. So far, no one knows which interpretation is correct. And that's the real story. Black holes sit at the fault line between general relativity and quantum mechanics, two theories that both work extraordinarily well, but refuse to agree with each other. Until we unify them, black holes will remain places where certainty ends. We once believed the speed of sound was unbreakable. We once thought atoms were indivisible. We once believed time flowed the same everywhere. Every time physics hit a wall, it turned out to be a door. Are black holes different? Maybe. Or maybe they're just another reminder that the universe is stranger than our instincts allow. Could anything fall into a black hole and return? Probably not in any future we can imagine. But physics has surprised us before. And at the edge of knowledge, where space collapses, time fractures, and reality itself bends, I wouldn't assume the universe has told us its final secret. If you enjoyed this exploration into the extremes of physics, consider subscribing. There's a lot more hiding at the edge of what we think we understand. I'll see you next time.